Okay, so in this series of videos, we are going to talk about fluid mechanics. And then today our topic is static equilibrium in fluids. Okay, so let's get started. Okay, so now you have a beaker, and then in your beaker you have some water here. You know that on the surface of the water, it can feel your atmospheric pressure. Okay, the value for atmospheric pressure is 1.01 times 10 power 5 Pascal. Okay, and then you know that actually we are going to derive the water pressure. Okay, the formula for the water pressure is rho gh. Okay, and then the pressure that you feel at the bottom of the beaker is PB. Okay, so you know that the force that you feel at the bottom of the cylindrical beaker is FB, and then FB equal to the atmospheric force plus the weight of the fluid in the beaker. Okay, and then you divide all the terms by area. Okay, so FB over A is the PB, the pressure you feel at the bottom, and then the atmospheric force over area is the atmospheric pressure. And then you know that the weight of the fluid is mg, and then mass is equal to density times volume, and then the volume divided by the area. Okay, the circular area here is the height of the water. Okay, so you know that the water pressure is rho gh, and then the atmospheric pressure is PAT, and then the pressure that you feel at the bottom is PB. Okay, so please determine the absolute pressure in a swimming pool at a depth of 1.5 meter. First and foremost, you should know that absolute pressure is the pressure measured from absolute vacuum. Okay, so in your vacuum you have no air molecules. When you have no air molecules, therefore the pressure is 0 Pascal. Okay, so absolute pressure is equal to the atmospheric pressure plus the water pressure. Okay, so the value for the atmospheric pressure is 1.01 times 10 power 5, and then the water pressure is rho gh. The density of the water is 1000 kilogram per meter cube, and then the gravitational acceleration is 9.81 meter per second, and then the height is 1.5 meter. So yeah, here you go, you get the absolute pressure. All right. Okay, so this is the simplest barometer. Okay, and then I believe that this is the first time ever in human history that we are able to create vacuum in a laboratory. Okay, so yeah, this is it. This is mercury, Hg. Okay, so you know that the presence of the atmospheric pressure, right, can actually push on the surface of the mercury. Okay, and therefore the mercury does not overflow. Okay, therefore the mercury does not flow out. Okay, so you know that the atmospheric pressure is equal to the rho gh, and then the rho here is the density of the mercury. Okay, and then the h is the height of this. Okay, the height of the mercury in the tube. Okay, and then at sea level, when the atmospheric pressure is 1.01 times 10 power 5 Pascal, the height is 760 millimeter. Okay, so if you go and take this barometer with you when you are climbing up a mountain, you know that the pressure you feel is decreasing, and therefore H will decrease also. Okay, so if the atmospheric pressure increases, then H will increase also, then H will exceed, okay, the value of this. Okay, 760 millimeter. Okay, so this is a pressure gauge. Okay, so this is a pressure gauge. Okay, so you have two limbs in the U-shaped tube here. Okay, and then this is point 1, this is point 2. And then you know that the end of the tube is open. That means what? That means the atmospheric pressure will will push on this surface, and then the atmospheric pressure will push this surface as well. Okay, so the pressure at point 1 is equal to the pressure at point 2 because they are at the same level, okay? And then you see the absolute pressure you feel at point 1 is the atmospheric pressure plus rho GH1, and then the rho is the density of water because here you have some water, and then this is mercury, okay? And then the pressure at point 2 is atmospheric pressure plus rho GH2, and then the rho here is the rho of Hg, okay, which is the mercury's density. Okay, so H2 is the height here. Okay, so you cancel out, and then you cancel out G here, then you get this formula. You know that the density of the water is much smaller than the density of the mercury. Okay, when this has a very low value and then this has a very high value, you know that H1 is greater than H2, okay? H1 is larger than H2, okay? So determine the absolute pressure of the air in the tire if the gauge placed on it gives a reading of 2.25 times 10 power 5 Pascal. Okay, so you know the absolute pressure of air is the atmospheric pressure plus the pressure that you have measured by using your gauge, okay? Okay, now assume that this is a very big swimming pool, okay? And then now you assume that this pool is filled with water, and then please find the pressure force acting on the wall BCGF, okay? So yeah, BCGF. First and foremost, you know that the water pressure is rho GH, okay, rho GY. Okay, so you know that actually the pressure acting here is the greatest, and then the pressure here is the lowest. So what do? You say, okay, pressure equal to force over area, and then dF equal to pressure dA, okay? dA is the area element of this very tiny strip, okay? This very tiny strip that you have drawn, okay? Okay, because dy is very small, therefore we can assume that the pressure acting on every single point in this tiny area element here is the same. So we assume that the pressure is rho gy, this is y, and then the pressure rho gy is acting on every single point in the strip here, okay? Here, okay? And then dA, the small area element is L times dy, okay? And then this is dF. dF is the very tiny amount of force acting in this area, in this tiny area only. And then now you are going to find the force against the whole wall. So what do? You do your integration, okay? So the y is from 0 to h. The y is from 0 to h, okay? Okay, so after you have done your integration, then you can arrive at this final formula. However, you can do some shortcut here, okay? You know that the water pressure is directly proportional to the depth of water, okay? The greater the depth of water, the greater the water pressure you feel. So you straight away say that, okay, the average pressure, which is the pressure acting in right the middle of the wall, okay? Here is rho GH over 2 because here is H over 2, okay? This is H over 2, this is H over 2. Okay, so you say that the force is the average pressure times the whole area, and then the whole area is LH, okay? Therefore, you can still arrive at the same formula. Okay, please calculate the torque on a submerged gate. Take the density of water to be 1000 kg per meter cube. Okay, so yeah, you see, this is a fixed wall. Okay, this is a fixed wall, and then this is your gate. Okay, this is your gate, and then these two are hinges. Okay, So the whole thing is submerged in the water. Okay, so you know that when there are some water here, the pressure force will add onto the gate and also onto the fixed wall as well. However, the wall is fixed, but then the gate will be pushed open like this. Okay, so when you have a force, you know that F equal to ma. When there is a force, there's a linear acceleration. So it's like this. Okay, linear acceleration when you have a force. Now, if you have a torque, then you will have an angular acceleration. That means that it will be like this. Okay, so from the side view, it's like this. Okay, so there will be an angular acceleration. Okay, so yeah, now you want to find the torque, right? First and foremost, you find a small force acting on a small area element. Okay, so for example, our small area element here is this red color strip. Okay, so you say that the pressure acting on this tiny area element is rho gy. Okay, so you know that a constant pressure of rho gy is acting on every single point in the tiny area element. Okay, the dA is the area of this tiny strip, okay, which is W, the width times the dy. Okay, dy is this one. Okay, this is dy. Okay, the width of this tiny strip here. Okay, so P equal to rho gy. Okay, y is calculated from the water level. Okay, from the water surface here. Okay, tau means torque. Okay, d tau equal to df times d is the shortest distance between this strip and this one. This is your axis of rotation. Okay, so we say d equal to y minus 2. Okay, so d is this one. Okay, and then like I said, d is the shortest distance between the point where you add your force on and the axis of rotation. And then when you hear the word shortest, you know that this is what? This is right angle. Okay, this is right angle. Okay, okay, so d is y minus 2. And then what is df, please? Df is this one. Okay, you bring everything here. Okay, so d tau, this is the small element of torque acting on this tiny strip only. And then now I want you to find the torque on the whole gate. Okay, the torque on the whole gate. Then what do? You do your integration. Y is from 2 meter until 4 meter. Okay, I repeat one more time. The lower limit for y is 2, and then the upper limit is 4, which is from here all the way to here. Okay, so this is how you calculate the torque. Okay, so in the next video we are going to discuss about Pascal principle. Thank you.